In an earlier video, we analyzed arsenic sulfide extended XAFS data using a Feff calculation for one scattering path. That single shell fit introduced many of the concepts for doing extended XAFS analysis with Feff calculations. In this video, we'll analyze a spectra with two paths, expanding our repertoire of extended XAFS analysis. Hi, I'm Matt Newville, and this is part of the video series for using Larch for XAFS analysis. In this video, we will run Feff on iron oxide, read in and process the XAFS data to KFK, and run Feffit with two scattering paths for iron oxygen and iron-iron scattering, and explore some of the options for doing Feff fitting. I think this is a more realistic example than doing a single shell fit, and it also expands our ability to test what we can do with the data. So let's start by reading in some data. I'll go find the iron oxygen data. So under Feffit, and there's the iron oxygen, you should be able to have these files downloaded from the site listed in the description below. So I'll read in the iron oxygen data. Just for now, I'm also going to do a trick where I'm going to rename this group just to be FEO. That will help the titles on all our plots look a little better. So that's just FEO. When we plot this with the data with the normalization looks pretty good. I won't go into too much detail of that. This data set, I should say, is not perfect. And we're going to analyze it up to about 15 universe angstroms. In fact, I'm going to cut this to sort of 14 or so, and let's look at the window function we're going to apply with that too. In fact, let's lower it a little bit. Maybe 13.5 is better. Okay, so that's the data we're going to analyze. This is iron oxygen. If I plot the Fourier transform of that, we have a shell that corresponds to iron oxygen and a shell that corresponds to iron-iron scattering. And then some higher shells that we could analyze, but we're just not going to do that in the interest of time here. There's enough material to go over. So we'll start with, we'll start by finding a Feff calculation for this data set. And so I'll go, here's our Feff Fitting tab. We're going to go, picks the range in K, the Fourier transform windowing function, and we'll work on the R range for the fit in a bit. First, let's bring in the Feff calculation. So I'm going to browse this CIF database that we have here, and I'm just going to pick something with iron and oxygen, including only those elements. We have several iron oxygen spectra or structures available here. You can see a lot of them are listed that are only iron and oxygen. I might just say, let's go find the woostite one. It's down here a bit. This one looks okay. All right, so this is iron oxide, FeO, in a cubic symmetry with iron and oxygens in the neighboring site. So with iron as the absorbing atom, and we'll do a K-edge calculation using Feffit. We'll go out to a cluster. Let's just say we go out to 6 angstroms. Then this is the Feff input file that we have. The potentials listing, so the K-edge is listed here. The control parameters to tell it how to calculate the XAFS. We don't need to go in much detail again for that. There's an iron absorber. There are iron scatterers, and then oxygen in the first shell at a distance of around 2.15 angstroms, and iron scattering at 3.04 angstroms or so. So let's just run Feff on that with that structure. And when it's done, it'll show us the paths that it's calculated. So there's an iron oxygen path with 6 equivalent paths. That's iron oxide. This structure of iron oxide is the rock salt structure. So cubic structure with 6 oxygen neighbors and 12 iron second neighbors. And then there are some multiple scattering paths and then a further oxygen distance. And we'll just leave that out. That would be to analyze this stuff out here. But for the iron-oxygen and iron-iron peaks, we only need these 2 paths. So that calculation is done. I'm going to put this away. And then, then once we've done that calculation, we can model this data set by importing paths from the Feff calculations. Right now we only have one listed. I cleared it out in the interim. But we're going to bring in now that iron-oxygen path and that iron scattering path. I would bring them both in. Why don't I start with just the first shell to mimic what we did to start with? It's always good to start with just 1 or 2 paths in the first shell. Let's just start with the first oxygen path only. So when this comes in, I'll put this away. When this comes in, it lists, as we saw for the arsenic sulfide data earlier, brings in a path that's oxygen at 2.16 angstroms, so that gives it a label of O216. It's read from the path that there's a degeneracy of 6, so it said that the amplitude was 6 times S0 squared, and S0 squared would be something that we can vary in the fit to optimize the data. There's an E0 parameter that will be evaluated using E0, just E0. Again, these can be expressions in terms of the variables, but right in this simple example, they're just the variables themselves. And a delta R variable, delta R O216, and a sigma squared O216. So we go over to the parameters tab. Here it lists those parameters that are available to be varied in the fit, and they're all fine values. And now we want to look at our data and think about what that might look like. So if I say plot the current model in R space, it will draw the model, the iron-oxygen scattering here in R space. And you can see that we should fit, it doesn't extend much past 2 angstroms, so we should probably only fit out to about 2 angstroms, which is also where this minimum in the XAFS chi of R is. As you can see, there's a little bit of bleeding of that shell, and we'll come back to that issue in a bit once we get to the iron. So we have that. We can fit this data then between 1 angstrom and 2 angstroms with these Fourier transform parameters. We're using a k weighting of 2. We're going to allow S0 squared to vary so that the amplitude is 6 times that S0 squared value. E0 will vary in the fit, and the R values will also be refined. So if I say fit the data, we get a fit that looks like this for the magnitude of chi of R. And if we look at the real part here, we zoom in on that, the fit looks pretty good. Especially between 1 and 2 angstroms where we told it to do the fit. There's something, a little bit of background subtraction stuff maybe still here that's not perfect. And anything above 2 angstroms we haven't fitted very well, but we weren't trying. So that looks, in principle, pretty good. If we now look at that in K space, though, chi of K, then an important point here is that red curve is the best fit to the data. It's only looking at the portion of the spectrum up to 2 angstroms, or between 1 and 2 angstroms. But that is the best fit. It looks like there's no real chance of anyone saying that that's obviously the best fit to the data, or that's even a good fit to the data. But because we're doing a Fourier analysis of it, that is in fact the best fit to this portion of that spectrum that's between 1 and 2 angstroms. It's just that in this spectrum, there's a lot of other stuff going on above 2 angstroms, especially between 2 and 3, say where there's this huge iron-iron scattering. So again, that is the best fit. It's not that that's an initial fit or a poor fit. That is the best fit. Now, if we look at the statistics for this, then there are 8 independent points from the information theory for that Fourier transform range, that K in R space, delta K, delta R, gives that number of independent points. We used 4 variables, so we're not oversampling the data. We're not trying to overinterpret the data. And we have a reduced chi-square that's about 2, which is actually not too bad. There are information criteria which are harder to interpret as absolute values, at least for me. Now, when we look at the variables that happened, now we get into some interesting and maybe problematic results. S0 squared here is 0.4. S0 squared is typically a number between about 0.7 and 1. So having a value that's below 0.5 is usually an indication that something is not quite right with the model or with the data set. E0 is a value refined by 2 electron volts. That's not too bad. Sigma squared is a positive value of 0.008 or 0.009 maybe, plus or minus 2. That seems acceptable. And delta R, though, is the distance for the oxygen scatterer refined by 0.07 angstroms. So if we look at the path parameters for this set, again, shows those values just as plain text, and then the distance that we started with at 2.15 or 2.16 angstroms refined to a value that is 2.09 angstroms. So it actually contracted quite a bit from what we started with. I'll tell you that I believe this data, which is fairly old and maybe not the best iron oxygen data available. It's what I have, and I'm happy to show an imperfect fit to imperfect data as part of the instructional aspect of this course. I believe this data might have some 3+ oxygen or 3+ iron in it. It's difficult to make stoichiometric FeO, and I think that might be part of what the problem with this data set is. Also, the amplitude factors are always come out low with this data set. So I think that this data may have, so it obviously has a few little glitches in it. I think it may actually also have been made not perfectly and have some pinhole effects, which will reduce the amplitude. So S0 squared, right now it refined to 0.4. I'll say that we can assert that it will be around 0.7 and maybe possibly lower for this data set to work out well. But that's just the first shell fit. And I think that we can conclude that we're not perfectly certain that we have that data set interpreted perfectly correctly. It looks like a pretty good fit, as if the iron oxygen was right for that. And the fit's not bad, but there's something for us to think about. One of the things to think about is just looking at this spectrum and looking at that fit in K-space is that, the iron-iron scattering for this path is kind of enormous, and we really ought to take that into account. In fact, if we add the iron-iron scattering, we might get a better fit, not only to the iron-iron portion, but also to the iron-oxygen. So let's go do that. Let's go browse the Feff calculations, and we'll go back to our iron woostite, that's FeO, and I'll add in that iron-iron scattering path. So I'll import that path, and it does the same thing. It gives a label. It says it's going to be 12 times S0 squared. In fact, it uses the same S0 squared and E0 parameters, but it's added different delta R's and sigma parameters for the iron-iron scattering. And if we plot that current model, again, starting with those values, here that looks like it's pretty good. It's going to model the iron-oxygen scattering and the iron-iron scattering. If we look at that in the real part, you can see that the things are pretty well in phase, so that it's going to fit without too much of a change in distance. Although that oxygen is still looking like it's a bit off. The iron-iron scattering looks like it's pretty good. And in K-space, this isn't the best fit, but we can see that we're getting most of those frequencies better. So that's even just a calculation with these values for the parameters that we know we're not going to refine out very well. So let's try that as a fit. So we're going to vary S0 squared and E0 and apply those to both paths equally, and then separate values for R and sigma squared for each path. And we should also check where are we going to do that fit over, and now that we've added the second path, we should include that we're going out to, say, maybe I'm going to click here and then here, and what's that? That's like 3.3. That's fine. I'll say 3.25 or so, just to give nice round numbers, and we can do a fit to that data set, and now we get a fit like this. That's a little bit better. That looks good for modeling both of those paths. Let's look at that in the real part of chi of R. We've done a pretty good job on that. Again, there's something in here that may not be perfect. And if we look at that in K-space, we see that we're doing a much better job. We can also plot each path individually. This is kind of a mess to see everything over each other, so add a vertical offset to that, so that the data and model are there in red, and the green is the oxygen scattering, peaking up at around 3 or 4 angstroms, and the iron peaking up at around 6 angstroms. If I go back, I think we did this for the arsenic sulfide, but if we go back to this page and look at the chi of R for, or plot f of k for the oxygen, we have f of k, the scattering factor that goes in front of the XAFS in the XAFS equation. For iron, oxygen peaks up at about 3 inverse angstroms, and the phase, which is a little bit harder to interpret, drops. It has a slope that's negative. Again, it starts from about 0, -4, and it goes at k of 20, it goes to about -20, so that its slope is approximately -1, which is what gives the half angstrom phase shift towards lower R when we plot the chi of R. That distance peaks up at about 1.6, indicating that the distance that corresponds to is not 1.6, but more like 2.1, and that's because of that phase shift that has a slope of about -1. Okay, so if we plot the f of k for oxygen, it looks like that peaking up at 3. If we plot the f of k for iron, it peaks up at higher k, about 6, and it's a little bit flatter. It still has a slope that's not exactly linear, but but the first approximation has a slope of -1. And so that peaks up at higher k. So when we go back to our fit page and plot the current model in k space, we see that the oxygen scattering peaks up at lower k than the iron peak. And that's just because of that f of k amplitude that works as an envelope function around that oscillatory part. You can also see that if I don't plot and just plot those two together, that we've taken care of most of the oscillations in the data, at least over the fit range. There are some little pieces here and there. Then there's a nice feature here at 6 angstroms where there's a beat that we're not taking care of. That's because that's too high of a frequency for what we've modeled. We would need to go out and model this stuff out here, which is lower amplitude, but not 0. We would need to model that in order to get all of the finest structure in the fine structure here. These two side bump, those two shoulders on that. So that's a pretty good fit. So now let's go look at the parameters, the fit statistics. The fit 0,1 is the most recent we did, so that's the one with now 6 variables, E0 sigma squared, E0 S0 squared, and delta R and sigma squared for the 2 paths. So 6 variables total out of 16 independent points, and a reduced chi-square that's around 4. So not terrible, but not perfect. And if we look at our parameters, there's sigma squareds that are perfectly plausible numbers, 0.01. Perfectly plausible. That means that sigma, the variance, or the standard error in the distance is around 0.1. So those distances are 2 and 3, plus with a width of 0.1 angstrom. 2 and 3 angstroms with widths of 0.1. Square that and you get 0.01 to give sigma squared. S0 is now 0.6 in order to get, now that when we asserted that the coordination number for oxygen was 6 and the coordination number for iron was 12, we get an S0 squared of 0.6, which is on the low side. Concerning, on the low side and concerning, but not dramatic. Delta R is also 0.04. Again, a little concerning, and the delta R for iron is actually a little bigger. That also is consistent with a little bit of 3+ iron, a little bit of hematite in the sample, in the spectrum. And if we look at our parameters page, or our simple report page, all of those numbers are here, and it also gives a nice table of values for R, now refined to 211 instead of 216. So definitely in further than I would like to see for something that was a standard that we thought we knew we had characterized well. And R for iron seems perfectly acceptable. One of the things that, though, that we did here for modeling this data that you may want to not do is we varied S0 squared. And that's something that you might want to do with a standard. But let me show you how, but a common question and something you would want to do for many data sets is to not vary S0 squared, but to assert S0 squared and vary the coordination number for each of the paths. So let me show you how that is done. So for the oxygen path, we said that the amplitude was 6, just the number 6, because that's what we knew the degeneracy to be, the number of equivalent paths, times this value S0 squared. Well, let's just change that to n. I'm going to change that to n sub O. Return. Actually, maybe I'll change that. Maybe I'll change that to NO216, just to be consistent with everybody else. So that's NO216 times S0 squared. Okay? And I'm going to do the same for iron, the iron path. Take this 12 and just make it be N Fe3O5. Now, I'm just asserting that there will be a variable, or at least a parameter, if there's we get to the difference between parameters and variables, called N times N underscore FeO305. So let's go to our parameters page and look at what we have, what that caused. As we type those in, those expressions that we typed in were parsed and filled in here. And in fact, there's something for NO, because I typed that and hit return. It was slightly accidental, and I don't want that. I'd rather have it be N for O216. I can just set that to be 6, at least as an initial guess. And I can set N for Fe3O5 to be 12, not 112, but 12. And I could say that those are variables in the fit. What I would do now is take this S0 squared. Obviously, the amplitude, or importantly, maybe not obviously, and importantly, the amplitudes that we have here are NO216 times S0 squared. And for iron, it's NFe3O5 times S0 squared. So N and S0 squared are completely correlated. If one goes up, the other one goes down. That's always going to be the case for XAFS. The S0 squared parameter is just a multiplicative factor in front of the N and the coordination number. Now we have two different paths and different parts of the data set. So S0 squared won't be completely correlated, but it will be very highly correlated for when you have two paths. So the normal thing that one would do is to analyze the spectrum of a well-known, well-characterized standard, assert that you know what n is for those scattering paths, and figure out fit what S0 squared is. That amplitude factor covers up a lot of issues in normalization. Like we had to pick a normalization in the edge step. And if that's off by 10%, then our coordination numbers will be off by 10%. So S0 squared can help mask that. In addition, because of each beamline, for if you're collecting data at a synchrotron, which most of the data here will be, each beamline has a slightly different energy resolution. And that's difficult or it's possible, but it's difficult, or rarely is modeled separately. And that goes into the amplitude factor as well. That broadens or smooths the data, the measurement, so that can be folded into an S0 squared. So varying the beamline, or the slits on the beamline, can change what the resulting S0 squared is. So often people will measure a standard under the same conditions and use the fit to the standard to get S0 squared. For this data set, I'm just going to assert that, I'm going to just pretend that I know that S0 squared should be 0.7 for this data set. And then I'm going to not vary it, I'm going to fix it. So we could do this fit. Now we have more variables. Because we're varying 1E0 and a delta R sigma squared and n for each path. So 3 variables per path, plus an extra. So 10 variables in all, I think, not 6. One of the things is I typed this N0 wrong, so it will vary this value, and that's not being used in the fit. So if I do a fit to this data, let's just try that. Let's see if this is all going to work. I'll do a fit to that data set. In fact, and one of the things, it gave a fit, and it got values, but the standard errors for them are not available. It should be better at reporting why that happened, but the reason that happened was because this one variable didn't change from its starting value, basically because it was unused in the fit. There was no place where we used n0, so it could try to adjust n0 and it had no impact in the fit. If we go to this Edit Parameters tab, here we can do a few things. And this can be useful for fitting for more complex models. This shows that we have S0 squared is fixed and all the other parameters that we have. But when it comes up, or if you click on the Select Unused Variables buttons, it will select all of the variables that are actually not used in any of the expressions for any of the paths that you currently have defined. So we can, with that checked, we can either remove them or fix it. We can just say fix that value to 1. Or since we know we're not using it, we can remove it. We can just remove that parameter. Yes. That will be fine, and now that parameter is out of the list. And now we have parameters that only select unused parameters. There aren't any. They're all being used in the fit. In this section, you can also add a new parameter that you can use for downstream calculations if you want to calculate other factors based on the values of the current parameter values. You can. I'll leave that aside for now. That's not highly useful for this data set. Let's go back here. So now we have the variables that we're going to use, and somehow I should make sure that that's 6 and that's 12 as the starting values. Again, it's not super important that those starting values are super close to the right values, but they should be close. Now, I can also assert that the coordination numbers should be positive. I can even assert that they're positive and less than 100. That would be a fine thing to do. Saying that, let me caution you that the bounds here really ought to be defining physical sense, not what you think is a reasonable set of values. So for delta R, don't make that be plus or minus 0.02, because it's likely to hit that boundary, those min and max values, and that will also make it difficult for the fit to continue when it hits the boundaries. It can process and continue. It may not be able to calculate the uncertainties in the parameters very well if it hits the boundary. So use these with caution. In fact, we could probably just leave all of these unbounded. It would probably be fine. I'll leave that one unbounded and bound that one just to see how it goes. So now we can do a fit to this data. It's going to work again. It's probably going to give the same results, but now the uncertainties will be calculated because all of the variables were used in the fit. In fact, if we look at these previous two, we had 8 variables before. That unused variable was listed, and so the chi-square, the actual fit, is identical, but reduced chi-square went down a little bit because we dropped one unused variable. And now we have our fit to the first 2 paths of iron oxide. We can look at the data in chi of k. Again, we've modeled this pretty well. I think that numerically the results for this are going to be very similar to what we saw before. Although if we look back at this was our fit when we varied S0 squared, but not the 2 distances independently. And this is our fit when we select that S0 squared is 0.7 and we'll vary the 2 coordination numbers. So the fit got a little bit better. Reduced chi-square went down, and these 2 information criteria values also went down. So it's a little bit better to have 2 different distances in this data set, or 2 different coordination numbers for this data set. And now we can look at what those results are. So the fit got a little better. That is to say, the fit got a little better even though we added a variable. It got better enough to justify adding that variable because reduced chi-square went down and our 2 information criteria went down. But there's still a sad result for this data set that the distance for iron oxygen is still a little bit on the low side. It's now it's about 211, whereas 215 or so would be a better value for woostite. And the coordination number, N, is about 4 instead of 6. The iron neighbors came out about right. So it's just the oxygen. So there's a little bit of oxygen at a shorter, that's lower in coordination number and shorter. Like there's some tetrahedral oxygen in this data set. So I think that's so those are our results, and I think that that's then a good place to say we've modeled iron oxide well. I guess I should plot these in all of the different spaces. So in R space, well, we looked at that in K space, but we didn't look at this in R space. In R space, I won't, without any vertical offset, we can see that this iron scattering, just like the oxygen sort of went above 2 angstroms, the iron actually goes below 2 angstroms, leaking into that first shell pretty dramatically. And in fact, if we look at that in chi of R and plot just those two paths, take out the data even and the model, it's difficult to see that where those two paths are really separate from each other. So in fact, when we look at the real part, I plot the real parts together. Now there's a lot of stuff on this page. Let me just plot the model as magnitude, and then the two paths together as magnitude. I'll take out the data. Just the magnitudes. It's difficult to say in this model why this dip at 2 angstroms happens. If we go back just all the way and just plot that, just plot the data, it looks like there's an iron oxygen shell and an iron shell. And I'll tell you that for many years, XAFS could only be analyzed by isolating shells. And so you would say the shells are separate at 2 angstroms. But you can see from this data that that's not really true, that the iron scattering leaks into the lower R portion of the spectrum, and that the iron oxygen is not done at 2, it's just mostly done. So that dip, that near zero intensity in the magnitude of chi of R doesn't really show up as obvious in the real part of chi of R or in the data. So using those, that's the data in chi of R, and using that dip as the separation point for the shells is a bit dangerous. I will also say that since we did this here, that the stopping end at 3 angstroms is probably, or 3.2 I think we did, is also questionable. There will be scattering from these parts of the spectrum that will also leak into this shell. So I would be willing to say that we have the oxygen pretty well underhand, although it didn't turn out as great results. But the iron, in order to get the iron scattering, I might want to at least have some small, or even if it's all fixed, at least some model of what's happening above that portion of the spectrum to get that well. We'll come back to this in a bit. Sometimes those dips in the spectra really are where the spectra are fully separate, and sometimes they aren't. So I think that I'll leave it there. We have a pretty good handle on how to fit 2 paths for iron oxygen or for a metal oxide. And I think that shows you how you would fit coordination number, fixing S0 squared and varying the coordination numbers, and how you can adjust the amplitude and other expressions for the path parameters and do the fit. So if you have any questions or comments on this, please leave them in the comment section below, and we'll see you in the next video. Thanks.